to Astronomy on Tap. We're going to get started pretty soon, but if you want to play trivia with us tonight, our super fast, brief trivia, please come get a trivia sheet and golf pencil from Barbara up at the front. Thank you.
You're muted for now.
Say something?
1, 2, 3.
Sam, do you want to announce the new projector that we're getting? Since you did all the work for it? Okay, I call you up. When we start.
No, I mean, would it make more sense to announce it when we actually have it, or just be like, this is the thing that we did?
I don't know. What do you think? I think it could be fun to announce just because a lot of people gave money and have no idea where that money has gone up until now.
Do you want to do that before or after trivia?
Before. Be ready. Let's over there.
I guess.
I'll just hand it to you. Get started. I'm gonna get started. Okay. Hello, everyone. Hello again. Thank you. Thank you. Good to see you all today on this fine day. It's so nice out. That's a really cute dog, by the way. Great dog. So welcome to Astronomy on Tap. We have one speaker this evening because I wanted to give him as much time as possible because it's going to be a really interesting talk. I will introduce him before the talk, but first we're going to do our usual round of trivia. So again, if you didn't get a trivia sheet and golf pencil from Barbara and you want to play, please do that now. But before we get started with trivia, I'm going to invite up my lovely co-host, Sam Charney, who will be taking over as full host, by the way, in September. Yeah. And Sam is going to tell you about where your money went.
All right. Don't go too far.
I will.
It's still on your hip.
I'll stay right here.
Hello. As Megan just said, I'm Sam Charney. I'll be taking over from Megan as the, lead, the host, the figurehead of Astronomy on Tap. Yeah, maybe that one. And so many of you have very generously donated funds to our fundraising donation drive, and we wanted to thank you again so much. We've put those funds to buy ourselves a projector. We're currently, thank you.
It was so needed.
We definitely needed it. So this one we're currently kind of stealing from the Utah Planetarium, and we don't want to be doing that for much longer. It's also very heavy. So we're getting a projector that is much lighter and has about the same capabilities, and will actually be a higher resolution because it's newer. So thank you all again very much for your donations. We couldn't have done it without you.
Yeah. I must say, I greatly enjoyed so for those of you who don't know, UW has obviously had some funding issues recently. And when we told them we wanted to buy a projector, they were like, what are you talking about? And then we got to come back and say, actually, we have money. We have our own money. So that was fantastic. Okay, so for those of you who don't know, here's how trivia works. I'm going to put 10 questions up on the screen in sequential order, and you will have 30 seconds to write down your answer. At the end, I'm going to time it. At the end, I'll go back and show you each question for 15 seconds, so you have 2 opportunities to get it down. Then we'll collect your sheets, and after the talk this evening, we will announce the trivia answers. Okay, are you guys ready to play trivia? Are you ready to play trivia?
There you go.
Okay, I'll talk about that later. Okay. Yeah, it's just Mario, you better know all of them. This is a hard one. Where should we have put the telescope? That's true.
Definitely getting fired from streaming starting in September.
I'm getting demoted to lead,
Promoted.
Right.
Promoted. Yeah.
Right. That's what they call it.
You're going to be the first Astronomy on Tap host that knows how to run the live stream. How does that feel?
Feels great.
I've never figured out how to mute this from What's wild is Jake just goes in and he's like, it's muted. I'm like, yeah. Just really Oh, I missed all of it.
It's okay. You're going to get a second chance to write down your answer.
Were you involved? We didn't fight it. No, I know. That's What's really funny is when Chester does trivia, there's always like one or two that may or may not be correct.
has been like. Okay, that was the first time through. So now we're going to go back through each slide for 15 seconds apiece. Now. Okay, hopefully you got them all right, and everybody can be winners. That's not reality though, but please bring your trivia sheets and golf pencils up to Barbara at the front so we can grade them. Do not forget the golf pencils. I would like them back. In other news, so our talk tonight is going to be featuring a lot of like really cool space pictures and stuff like that. And obviously, the projector is improved to what we used to have, but it's not perfect. So if you did want to be able to see those pictures in like high resolution with all of their colors and stuff, this is the link to the YouTube live stream that we put up, and you'll be able to follow along with the slides there if you want to see those pictures. So I'll just leave it up for a few more seconds before we switch over to the slides. Okay, I'm going to switch over to the speaker slides, and I'll be back in 3 seconds. Do you want this clicker? You have one? Okay. So here is the Hopefully everybody got their trivia sheets in. So at this time, I'm going to introduce the talk and the speaker. So tonight we have Professor Dr. Mario Juric, who is going to be talking to us about welcoming a new era of cosmic discovery. So for those of you who have been online like at all in the last couple of weeks, you've heard that the Rubin Observatory is up and running. It is taking images. That's absolutely cause for applause. Yeah. That's fantastic. So Rubin has been covered by pretty much any news outlet you can think of, all the way from the New York Times to more science-focused outlets. And what's interesting for us here in Seattle is that Rubin is actually headed at the University of Washington. So we have a whole fleet of people who are extremely qualified to talk about Rubin Observatory and LSST. So Professor Juric is the leader of the DiRAC Institute, which is a data-intensive research astronomy institute at the University of Washington. And he is also the leader of data management for LSST, the Legacy Survey of Space and Time, which is going to be completed with Rubin. And something else that Mario is very well known for is being extremely tall. He is the tallest person in Seattle, so that's pretty cool. Okay, so without further ado, here's Professor Juric.
All right, thanks, Megan. Thank you for inviting me. A couple of things. So the first thing is, usually there's 2 talks. My students know that I have no ability to keep time, so that's why they give me the full 2 slots, not because they're nice, but because they're trying to spare you of an incredibly long talk. The other thing is, let's just get a couple of questions out of the way. I'm 6'8". I do not play basketball, and I cannot show up at your birthday party dressed as Chewbacca. Now we can start talking about astronomy. So, maybe. There we go. So I'll tell you about this new telescope that we built called the Rubin Observatory and what it's going to do over the next couple of years, basically a decade. But I want to start with an introduction that kind of will lead us to how this observatory was built and why. So I want to talk a little bit about what do astronomers do today. And if you ask what's an astronomer, usually these days if you ask something, you go to Google or you go to ChatGPT and ask it. So here I went to Google. I hate reading, so I went to Google image search. And if you ask for what an astronomer is, this is the kind of image you get. It's a person standing next to a telescope observing the skies. And that is not far from the truth, or at least it wasn't far from the truth for a while. What people think astronomers do is what we did for hundreds of years. We would build these telescopes at mountaintops, the bigger the better. We would go there, we would take images, take photographs. Who here remembers photographs like on film? There we go. This is just a very large version of one. We would take those images over the entire night, we would bring them back home, we'd develop them, we'd look at them with these eyepieces, and then you discover something interesting, you have more telescope time, and rinse repeat, the process continues. Things have changed a bit. What we increasingly do, rather than having an idea which object to watch and observe and go into a telescope, is we build telescopes that instead can observe almost the entire sky for us. Here's an example of one called the Sloan Digital Sky Survey Telescope. It's in New Mexico. I'll show it to you in a bit. Then we build huge cameras. That thing you have in your pocket on your phone, this is the same camera, but the astronomical version. It's huge because it has lots and lots more pixels. We put these cameras onto telescopes like these, and then we collect so much data that we cannot look at them anymore. Not because we wouldn't want to, but literally you cannot, there's too much. So then we write software. We write computers, we teach computers how to look at those images, identify objects, tell us what's interesting, and ultimately populate huge databases that we all can go query online, and that's how we do science. So to give you a sense when I say that these telescopes can observe vast amounts of sky, to give you a sense of how much, let's go through this exercise. How many of you have seen this picture somewhere? Wow, almost everyone. This is one of the most iconic astronomy images, I think, over the last 25 years. It's called Pillars of Creation. It's in the Eagle Nebula. Oh, what happened here? Eagle, not evil. And this one was taken with the Hubble Space Telescope. And if you know which episode to look for, it appears in Star Trek: The Next Generation on one of the screens on the bridge. So, but how many of you know how big is this actually in the sky? It's this big. So this is the moon. This entire image that we all spent looking for years is that big in the sky. It's tiny. And that telescope that I showed you, one image that it takes, this telescope, is that big. So that's the difference with this new generation of telescopes. They can observe a huge amount of sky at the same time relative to the telescopes we used to build before. And then what do you do when you can do that? Well, you take many images and you go and observe the entire sky. And that's what the Sloan Digital Sky Survey did. This telescope was built in the late 1990s, almost as an experiment. I think it went bankrupt 4 times before it finally managed to see the sky, and then it changed astronomy after that. It collected 20 terabytes of data over 10 years. It collected information about 1.2 billion stars and galaxies. And as you'll see in a second, this is the most cited telescope on Earth right now. So what did it do? Here's the photo of the telescope. We love it. It's on an observatory where UW is one of the major partners. It's in New Mexico. It is on a terrible site for astronomy. How do you know that? Look at all the trees around that place. If there are trees, it means it rains. Rain not good for us. So here's what SDSS discovered. It discovered most distant known quasars. It built the most distant map of the Milky Way. It discovered that Milky Way is gobbling up smaller galaxies, found the most dark matter-dominated galaxies. It found a galaxy that has only about a dozen stars, and they float in a ball of dark matter, effectively. And all of these things are not bad from what is essentially a small telescope in a terrible site. Just how not bad it was? Here's a website that we go to figure out whether our telescopes have justified the funds that we used to build them. You go here and you ask for how many papers mentioned in SDSS or Sloan survey or blah blah blah, and it turns out there's 3,000 papers written with data from this telescope with 237,000 citations. Now, the right thing for you to ask me right now is that big or is that small? So let's compare it to something that we know has made a difference in astronomy. Let's compare it to the Hubble Space Telescope. So these are the same numbers for the Hubble. In terms of numbers of papers, they're roughly the same. In terms of the number of citations, the SDSS is actually slightly ahead. But in terms of impact, they're roughly the same. So we got what you could call the crowning achievement or crown jewel of world astronomy from the late 20th century versus this telescope that was in a pretty bad site. It was experimental. It was really hard to get it running. And that's what it did. And why did it do it? Because it managed to cover the entire sky and enable all sorts of science to be done. So this was our hint, and University of Washington was one of the major partners on this telescope. That's how we got into this business. So this was our hint that this is a good idea because it costs, I think, about 1% of this telescope. And as Megan said, University of Washington is kind of in the 1% level of money right now. So we decided, when we were trying to decide what to do next, we said, all right, so for our next trick, if this thing worked so well, and it was an experimental telescope at a bad location, it was a small telescope, it didn't cover exactly the entire sky, what are we going to do next? Well, let's build an observatory that's now in a good location, that's big, that has a huge camera, that can cover the entire visible sky, and it can do it as deep as the largest observatories can right now. And that is the Rubin Observatory. And we were working on this for the last, I kid you not, 20 years. And finally, it got its first images a couple of months ago, and we were able to show them in, I think, what was it now, 4 weeks ago. And that's what I'm going to show you in the rest of the talk. But that's the idea. We want to build a big telescope with a large mirror, largest digital camera in the world that can quickly scan the sky. And then what are we going to do with it? We're going to create an ultra-wide, ultra-high definition, 10-year-long time-lapse movie of the sky and a database of everything in it. And then once we have that, all of us, including you, so don't leave because at the end I'm going to show you the including you part, how you can get involved, can learn about the universe, everything from killer asteroids to what dark energy is. Okay, so here's our big, beautiful telescope. It's on top of a mountain in Chile. It's on Cerro Pachon. Who got Cerro Pachon right on the trivia question? Yay, go for it. By the way, if you got everything right on the trivia, you can leave right now. You know everything. You're not going to hear anything new from me. This is the largest sky survey facility in the world. These are trucks, and they're big trucks. That's the size of the telescope. So where is it? It's in Chile. It's kind of a central or slightly northern part of Chile. It's about 40 kilometers away from a place called La Serena on a mountaintop. It takes about 2 hours to get there. Very scenic ride. Not great if you suffer from motion sickness. All I'm going to say. Co-founded by us at University of Washington and 3 other institutions, but now this is the national ground-based astronomy flagship in the US. This is how the observatory was built over the last 10 years. I love how this starts because it starts with a bang. We literally cut off the top of the mountain to get this done. I mean, not me, they won't let me touch explosives, but somebody did. And then, starting in 2014, the construction started. You can see the place where the telescope will be mounted. This is where the dome is going to go. And it's growing up and up and up. Everything was great. 2018 was great. 2019 then came. It was great. We were thinking we were going to start in 2021. Then things happened. Then we got a bit delayed. So here's 2019. And now you can see the dome rotating even before we put the roof over our heads. And then this ends in I think 2021 because they wouldn't let us go back up to the summit for almost 2 years. But then in 2023, the telescope was completed. Or the observatory, the building was completed. So now we get to step inside of that building, and you could already see through that opening that inside is a telescope. This here is the 8.4 meter Simone survey telescope, the largest survey telescope in the world. Simone comes from the name. Charles Simone was one of the early donors of the project. Fun fact: this project would not have happened without Puget Sound and Seattle area, because when we started back in 2003, and the scientists were very excited about it. The agencies usually fund these kinds of things were, let's say, skeptical, because it sounded too crazy. You're going to image the entire sky, and then you're going to build this data system to process it and so on. So what do you do in that situation? Well, you go to someone who's built big computing and understands computers and loves astronomy. It turns out there are many people like that in the Seattle area, including folks like Bill Gates and Charles Simone. So thanks to them, we started the early R&D, did the early R&D, and built the mirror on this project to prove that it can be done. And 20 years later, we have a $1 billion observatory up on the mountain in Chile. So whenever you use Office or MS Windows, thank you, because that enabled this thing to happen. All right, so here's that telescope in motion. When I say it's big and so on, what I should really be saying is it's fast. This here is 250 tons of glass and steel. Look how fast it's moving. There's a person over there. This thing is huge. That's real time. This is not a time lapse. So it can rotate 180 degrees, start, move, stop, be ready to take the next image in 18 seconds. When it's rotating, if it's looking downwards, the top is moving faster than 11 meters per second. If you're the fastest man in the world, the fastest 100-meter dash sprinter, you cannot outrun it. So when it's rotating, nobody's usually allowed in the dome. It's just too dangerous. This is what sits in the center of that telescope. This is the big mirror. This was when it came out of the oven. Well, we'll let it cool down a bit. But to give you a sense for how big this is, we keep using these words like 8 meters and so on, but you get a feeling for it when you see people around it. Here's our current director, Željko Ivezić, about 20 years younger when this picture was taken. And the other thing you see here are the people. So there's about 50 people around this mirror, and that was back then in 2008. Now there's more than 300 people working directly on this observatory, and then thousands of astronomers around the world helping with all kinds of research. So this mirror is now been completed. It's in the telescope. And this is the crown jewel. This is the camera. So take up your iPhone. Look at that little camera behind it. That's my camera. My camera is bigger than your camera. This camera has 3,200 megapixels, or as we like to say, 3.2 gigapixels. And if you wanted to project one image taken with this camera with TVs, it would take you 400 Ultra HD TVs. I was really annoyed when 4K came out, because before that I would say 1,600 TVs, and then the resolution went up, so we had to lower it. But still, this is something like a basketball court full of TVs. Like that's how big things would have to be. The field of view is huge, 45 times the area of the full moon. So that's the full moon in the sky. And when we take a picture, well, if we did this, we'd probably all get fired, because the moon is way too bright for this camera. But if we imagine we did that, this is how big the moon would be. That camera is big in person. Here's how big. This was when it was being finished still at SLAC. October, we're there in October 2022. That's 3 years now. That's the size. And if you're kind of skeptical, maybe this person here is, I don't know, exceptionally small or exceptionally tall. If you ever fly regional jets and you look at one of those engines under the wings, this here is Embraer, I think E175. I tried to find the engine that's exactly the size of the camera. This is as close as I got. This engine under the wings is the size of our camera. The camera kind of looks like a jet engine. So it's a big piece of equipment, 3.2 tons. Okay, so now we've got those pieces, we got those components, and we have the fastest sky scanner in history. We got the largest wide field camera ever built. We've got a super fast telescope that can take images, move to the next point in the sky, take another image, and just keep doing that. And you combine that with a huge mirror. We have the ability to see faint objects across the entire southern sky. We're in the best place for this telescope in the world. The Chilean Andes are high on top. I didn't mention it, but when I was showing you the video of the observatory, how many trees have you seen? No trees. It's great. So what we can do with this is now we can go ahead and we have the capacity to build the greatest map of the universe ever made, to go and image everything from near-Earth asteroids out to as close as we can get to the Big Bang with this telescope. And that's what we're going to do. So we're going to take a high-resolution, deep image of the visible sky from Chile. And when you assemble all those images that we individually take for just one covering of the sky, that would be an image of 10 million megapixels. So this is a 10 terapixel image that we're going to be producing. We're not going to just take one, because that wouldn't be cool enough. Now, we can do better. We're going to do this 800 times. So we're going to, you can think of this as an 800 frame movie of the sky, a stop motion animation of the sky in a way, each one having 10 terapixels. And what can you do with this? We think we're going to measure tens of billions of objects, roughly 20 billion galaxies, roughly 17 billion stars in the Milky Way, millions of asteroids, and we're going to measure them over and over again, at least 800 times each. So we're going to have tens of trillions of measurements of those objects. We're going to know almost everything that's been going on in the sky for the next 10 years. We're going to put that in a database, and we're going to make that available to the entire world to do science with it. So that's what this is. And the name of this thing is the Legacy Survey of Space and Time. LS spells LSST. Ask me in the questions why was it important for this to spell LSST. But that is going to be the data set, the legacy data set from this telescope. And I started with SDSS, the telescope that changed astronomy, because it showed it's possible to do these kinds of big projects. How does this compare to SDSS? So it took 10 years for SDSS to image this, approximately 20 terabytes of raw imaging data. With Rubin, this is one night. So if you got 20 terabytes, you got it right in the quiz. Okay, so these are promises, but now we built the observatory and we started taking images, and how does it look? We had our first photon, the first time the camera has seen the sky with the full system on April 15th, 2025. So that's now, it feels like a million years ago to me, trust me, but it's been only a couple of months. And initially, they wouldn't let us show the images to anyone. So all I could show, and Megan asked me to give this talk in April, and I'm thinking, no, let's wait a little bit, because if I were giving this talk in April, it would kind of end here. I would show you this. I would show you the reaction video, like like those things on YouTube, right? So this is the first image. This is the atmosphere in the dome. People seem happy. The boss seems very happy. This is Željko Ivezić, a professor here at the University of Washington and the director of the project. So you could tell that this looked good. But if I were doing this in April, this is where I would have to stop, and like we'd go and drink beers, and that would be it, because I wouldn't be able to show you the images. But now we can show you the images. So on July 23rd, 2025, the Rubin had what we call the first look event, when we were able to share some of the first images taken within the first 2 weeks of the telescope seeing the sky with the world. And that's what I'm going to show you now. Now, these images are all huge. So it's actually difficult to present them in the right way. So what we did was we created a movie of just zooming in, panning and scanning and moving around the images, and that's how we're going to be showing them. All right, so let's get ready. Here it is. So what you're about to see is near the constellation of Virgo. These are all galaxies. These are depths that are usually need a Hubble Space Telescope for. But it's not just one galaxy or a few galaxies, it's millions. And as we move around, we can see the diversity. You can look at, here's a barred galaxy, here's an elliptical one. You can see different colors. I'll tell you a little bit in a second what that means. But the most impressive thing to me is just the sheer numbers. And then the really impressive thing is, now we're going to zoom out. This is only effectively 2.5 pointings of LSST. So, and we can do each one of those, that snapshot, in 30 seconds. All right, so that was cool. You can go to skyviewer.app and browse through this large image, zoom in, zoom out, see all the details. But I'm going to go ahead and I'm going to pause here for a second, and then I'm going to show you some of those details. And because it's hard to tell, there's so much things going on this image that it's impossible to just narrate it in 30 seconds. So let's do that now. So here's a cutout out of that movie that we just seen. What do we see here? We see thousands of nearby galaxies. Nearby means these large galaxies in a place called the Virgo Cluster. It's a very large cluster of galaxies. You think of it as, I don't know, galactic village, galactic city. There's about at least 1,500 large ones in there. It's about 50 million light years away. So when the light that you're observing here started going towards us, the dinosaurs were only about 15 million years dead. The depth here is 26.5 magnitude. If you're an amateur astronomer, you're going to be impressed. If you're not, it's a number. It's very faint. But let's look at the details. What do we see? So first thing is, you'll notice that there are some objects that clearly look like galaxies, and there are these other things that look like dots. Well, those dots are galaxies as well. When you zoom in, you're going to be able to resolve many of them. So most of the things we see here are galaxies, because when you go to these kinds of depths, our galaxy, the Milky Way, runs out of stars. There's nothing that faint, basically. All right, so let's go browse a little. So look at this thing here. Those are 4 galaxies that are in the process of colliding. So think of a galaxy like the Milky Way, and I think about 4 of them, and think about them getting entangled, and then eventually they'll merge into one big, large galaxy. All this fuzz that you see around here, that's not gas, that's not dust, that's stars. That's billions and billions of stars that are just too far to be resolved. What do you see down here? you see a small cluster also of galaxies. There are galaxies that are just very close to each other. And in this image, this whole thing is a nearby cluster. What you don't see is what keeps it together. Everything you see here is only about 10% of the matter in that cluster. The other 90% is dark matter. But by looking at how this whole area looks, we can say something, we can learn something about that dark matter in here. But then look over here. You're going to see a couple of red dots. Well, more than a couple, depending on, maybe none, maybe more than a couple, depending on how far you are from the projector. This here is a cluster of galaxies as well. And that one's farther out. And one of the ways you can tell it's farther out is, well, this one seems a bit larger, so this one is smaller, so you think it's more distant. But also look at their colors. This one here is kind of yellowish brown, whereas this one is very red. Every galaxy here is very red. When we talk about redshift, you can see it here, literally with your own eyes. These galaxies are red because the light that started from them and has been coming towards us, got redshifted, got turned more and more red as it was passing through the universe because of expansion. So that's one of the, I've been teaching this for 20 years, and now I open up this image and I can literally see redshift. That's brilliant. Now look at these two galaxies. They're nearby spirals. They're just like the Milky Way. We just happen to be right on top of them, so we can see them from the above. This one here is more like the Milky Way than the other one. It has a little bit of a bar. Milky Way has a bar. And then if you squint, you're going to see they're speckled with these little blue dots. Those blue dots are stars forming. They're not individual stars. There are millions of stars forming at once, but the way they form is they form in these big clusters. Like think of them as families of stars just getting born all at the same time. And that's why we see them millions of light years away. So in this one image, you can talk about everything from cosmology, where the dark matter is, to how galaxies evolve, how galaxies form, to how stars form. That's the sort of thing we're going to be able to do with this telescope. And then everything I just talked about was this big in that image that I've shown you. And then this entire image that I've shown you is only 0.13% of the final image we're going to take by a couple of years from now. And there's about 5 million objects in here, and by the time we get through to taking our final image, we're going to have about 40 billion. So we're going to know what's going on in the universe and be able to hopefully understand why it's happening, what's happening out there. So this is why we were all so happy when we saw that first image in the dome, because we knew this was going to happen. After 20 years, we knew we had a telescope that can do this. All right, so what kinds of things can it do? 95% of the universe remains a mystery. It consists of dark matter and dark energy. We were really confused about dark matter for about 50 years because we didn't know what it was. So the universe decided to make us even more confused. It gave us dark energy. We used to think that we understood 10% of the universe because 90% was dark matter, and then it turned out there's dark energy, so now we know even less. By the time Rubin is done, this number will be like 99%. Rubin will detect about 20 billion galaxies, and by studying these, joking aside, we really do hope to crack what these two things are. And the other thing, as we're taking images, we're also seeing the Milky Way, the stars in the Milky Way. We're going to see about 17 billion stars in the Milky Way. That is, somebody told me this, and I really should check it, but it sounds right, so I'm just going to keep repeating it uncritically. 17 billion is apparently more than the number of people that have ever lived, number of humans that have ever lived. So we could go ahead and start naming each one of them, not just after you and your kids, but after every one of your ancestors, all the way down to Homo, whichever one you care about. I'm not sure where to draw the line between our ancestors and us. So we'll use this to build a 3D map that's 100 times larger of the Milky Way than the previous survey. 17 billion means roughly that we're going to see about 10% of everything that's in Milky Way. It's quite impressive given half of the Milky Way is hidden behind the dust and gas that we can't see through. And it'll help us understand how stars live, how stars form, and how they die. And let's look at these two galaxies that I showed you at the end previously with little specks of star formation, these blue dots. Now, I zoomed in here on these galaxies, but this is roughly as far as the zoom goes on this telescope. I cannot zoom even further to resolve this. But what I can do is I can find a place in our own galaxy where something like this is happening and go there. So that's what we did next. So this is now an image, it's same thing, of nebulae called Trifid and Lagoon. These are stellar nurseries. These are places where stars are being born in our galaxy right now. This blue light that you see, that's young stars. This red light, it's reflected stars, it's reflected light off of dust, also the stars. And look at how we can zoom out, we can pan, we can go and study every individual speck we see here. Those are all stars. We can study these bright ones. Folks who care about stars just look at this image and go like, yay! And while this is going on, I should mention, this was a test of the telescope. This is not even as best as we can. This was taken 2 weeks after the first image, and it takes a bit of time to tune all of this. So that's an example of what we can do in our galaxy. We're going to cover the entire galactic plane. We're going to see all of these places, and we'll be able to find places where stars are being born and then track them as they're starting their lives in a way. So I think I said that. Both nebulae are stellar nurseries where stars are being formed from clouds of gas and dust. So these are spectacular, but they're quote-unquote just stills from a movie. Rubin can also observe changes in the universe, and that's what I'm going to show you next. So we've taken we made those images that I've shown you by taking a number of separate exposures and then adding them together. But what happens if you don't add them together? Then you start noticing things that have changed. So that is this next example. So now I'm going to go back to that first image that I showed you, and we're going to zoom into a couple of stars. And now we're going to look what they do depending on when you look at them. So here's a star on May 3rd. Here it is later. It got brighter. Of course, how do we find these? We don't find them by looking, but we train computers to go look for changes. Here's another example. There's a blue star, and for some reason it was fainter here, and now it got 10% brighter. And then you do that over and over again. You can, I think we're going to show one more. Here's another blue star that did the same thing. So this tells us two things. First, it shows us that the universe is changing. Here's how many were found in total here in this field. It tells the universe is changing. But it also allows us to detect, but it also lets us recognize these changes as something we know. And in this case, these changes were coming, these things that were changing were stars that are a particular type of variable star called RR Lyra. They're about half to about 70% as massive as the sun. They used to be kind of like the sun. You can think of them that way. But they're twice as old. So they're in their old age now. And when stars get old, stars get bloated. Do not generalize this to people. I'm not trying to say anything. And they get brighter. So the older I get, the brighter I get. 40 to 80 times brighter. And the really neat thing with these stars, because they're so bright, you can see them far out. And we know how distant they are. When we see how they vary, we know how far they are. It's take my course at UW and I'll explain the details. But using this is how we can build maps of the Milky Way. This is how we can add a third dimension. So here's an example of from one of our students from some time ago, building a map very far, in just one slice, very far from the Milky Way and discovering a small dwarf galaxy that was being torn apart at the outskirts. So this is an example of how we're going to do this with Rubin, but now just not in a small slice, but over the entire sky. And there's much, much more than RR Lyrae. I'm just going to show you some visualizations of things that we only have a couple of examples today, but with Rubin, we're going to be finding thousands and tens of thousands of these objects. Here's an example of a star orbiting a black hole. And the black hole has what's called an accretion disk, and that accretion disk can sometimes overflow with matter and then start this huge jet. And when this jet happens, it brightens up and we see it. And then we can study what's going on around black holes. Here's an even bigger black hole. Any fans of interstellar here? Yeah, like you recognize this. The reason why I love showing these images is because they actually consulted a real-life bona fide astrophysicist to build these simulations for interstellar, so they're actually pretty accurate. Large supermassive black holes also have disks. Those disks vary. They're in the centers of galaxies. By studying how they vary, we figure out how big they are. Then you have things like this. These are smaller black holes, but sometimes, usually you don't want to get in the neighborhood of black hole. If you make that mistake, you're going to see what happens. Here's a star that made the mistake. It's approaching black hole. It's a blue star. Look what is happening to it. It's getting shredded into pieces, and boom. That's your star now. When that happens on our sky, it looks like an explosion. This is what's called a tidal disruption event. Imagine that. You take something the size of a sun, and in seconds, you shred it into pieces. So we're going to find, a few of these have been found so far. This is a galaxy, and then this little dot here is a tidal disruption event. It's not a galaxy, not a little dot. It becomes brighter than the entire galaxy for a moment. We're going to find probably thousands of these. And then to give you something closer to home, the other thing that changes in the sky are comets. Planets move, they're too bright, but comets we love. So here's an example. I forget which comet this is. We usually get a couple a year. With LSST, once Rubin starts operating fully, it should be at least an order of 100 per year. We're going to be finding lots and lots of comets. And one thing that's different also about comets is, relative to everything else I showed, is they're close. They're in our solar system. And so the last thing I'm going to show you is this. Rubin is going to be probably the best machine we've ever built in history to map the solar system. We're going to figure out where all those asteroids are, where comets are. We're going to figure out if there are places where we thought there aren't any asteroids, but there are. We're going to figure out if there are any asteroids that might be coming towards us with bad intentions. We might figure out if there are more planets. The best solar system ever. So how do we find asteroids? That image at the beginning that I've shown you of Virgo, well, it wasn't just stars and galaxies there. That right there is an asteroid. How do we know it's an asteroid? Because we take a little movie of the sky and we see it move. These are all new asteroids that Rubin discovered. So we start with 3, we go up to 6 by 6. There's a lot more than that. We just ran out of patience trying to make cutouts of all of them. These are all the asteroids that we discovered only in that small region. So by second night, we had 1,300. By third night, we had 1,600. Fourth night, 1,600, and so on. And remember, this is 0.13% of everything this telescope is going to do. Now, once you add the third dimension and try to visualize where this is in the solar system, this is where it is. This is the main asteroid belt where most of them live, and this is where we observed and found 2,000 new ones. Again, as a test. So you can go and view that at orbitviewer.app. There's a nice app that will show you effectively what I've shown you here at the end of this movie with nice 3D animation and show you where those asteroids are. But what's more impressive is what's going to come with this. So let me kind of recap and give you a sense of like, why am I so excited about a bunch of dots moving on the screen? In a few nights of observing, we found exactly 2,104 asteroids. Is that impressive or not? Well, before Rubin, the whole world will typically find about 20,000 asteroids each year. We did this in, I think, 3 days, 4 maybe. So we are going to, in a year, we're going to, in about a week, discover much more than the entire world discovers in a year. We already have. I just can't talk about it. So Rubin is a game changer for mapping the solar system. Here's something that Jake Kurlander, one of our grad students, his simulation that he built of, now you're looking at the solar system up from top. Here's the Earth with our telescope on it, and here's how the telescope discovers asteroids in the solar system. So I'm going to go and rewind this now that you know what you're looking at. Here's the survey starts, boom. In a month, we scan almost a third of the solar system. And we continue. as the Earth goes around, we scan more and more. This is like a radar for the solar system. It finds everything, and these are the discoveries. By the end of year one, we find about at least 1.5 million objects. And remember that number, because I'll give you a sense of scale in a second. Because of this, our picture of the solar system is really going to change soon. There are 1.5 million objects known today in the solar system. It took 225 years to find that 1.5 million. We're going to double that in the next year. And as the survey continues over 10 years, that total is going to go up to about 5 million. And the reason why almost everything, like we double it in the year and then it takes a long time to find the others, you think about it. You're moving as a radar beam through the solar system, and in the first year, it just takes you 1 year to scan everything, and then the rest of the time, you're kind of catching things that have fallen through the cracks. So this is one of the things, I think I said somewhere that this is going to be a 10-year survey, but you don't have to wait for 10 years for cool stuff to start showing up. Almost everything, a lot of action happens in the first year, especially in the solar system, a lot of discoveries. Why does this matter? That's the next thing you're going to ask me. Well, here's the practical reason. Some of these asteroids come close to the Earth. And as dinosaurs discovered 65 million years ago, you better have a space program when one of them comes too close. They didn't. There's about 25,000 of these so-called near-Earth objects known right now. By the time we're done, we're going to know about where 125,000 of them are. And we'll know, this is the important part, where about 80% of the dangerous ones are. These are the really large ones that come really close to the Earth. Right now, we know between about 35 to 40%. So we're going to double the number, or if you think about it in terms of risk, we're going to reduce the risk by a factor of 3 over where it is right now. All right, let's say you're not practical, you're an astronomer instead, and you just want to know, how did the solar system form? Where did water, for example, come in the solar system? Where did water come from? On Earth. One of the places we think it has come from are comets. The other one are asteroids. But nobody really knows how much water there is on asteroids. This is the kind of thing we can discover with Rubin. We can look at which asteroids suddenly start sprouting tails because they've got little geysers of water that keep popping up. That's the kind of thing that you can do when you have 1 billion observations of them. Then the next thing we can do is we can ask questions like, what happens when asteroids collide? We know the answer to that already. They shatter into bits and pieces. What happens to those pieces? So the reason why I'm showing you this slide is because we found one of those pieces just last week, and the paper about that is going to go out tomorrow. For those of you to whose emails I didn't respond to, that's why. We've been busy. This is work by Sarah Greenstreet from UW in our lab, and Chester Lee, who's our student here. Chester, I understand, was responsible for your quiz. So that's why the quiz was hard. He knows all about this stuff. Dmitry and Devanshi. Hey, Devanshi. So what have they been looking at? They were looking at those asteroids. Remember how I showed you our Lyra, that they're changing their brightness? Well, asteroids change brightness too. Why do asteroids change brightness? Because they spin. As they spin, you see more or less of it, and it's brighter or fainter. If you look at how they spin, you can figure out how quickly if you look at how they change brightness, you can figure out how quickly they spin. If you look at how bright they are, you can figure out how big they are. So this team here found an asteroid that's 1/2 mile in diameter, that's close to one of these families that got exploded or collided, and that spins once every 13 minutes. That is super fast when it comes to essentially mountains in space. And this is, I think, the first detection of something like that far away from the Earth. So far, we didn't have telescopes that could go faint enough to find these small spinning shards of asteroids that are falling apart this far out. And by finding these, we can figure out what asteroids are made of. Because if you're made of, let's say, if you're a big piece of iron, you're not going to fall apart into 1 billion pieces that are rotating quickly. You're going to fall apart into a smaller number of pieces. If you're a piece of clay, you're going to fall apart in a different number of pieces. So again, course at UW. But this is why this is exciting, and this should get published, I think, in the next couple of days. So let's go further out. Who here misses Pluto? All right. Do you have kids? Okay, let me explain to you once and for all, again, why we had to demote Pluto. Pluto used to be a planet. It's far out here in the region behind Neptune that we now call the Kuiper Belt. Why do we call it Kuiper Belt? Because we found 4,000 things orbiting over there. Pluto just at the time happened to be the largest thing. Here's Pluto. Here's its moon, Karen. How many of you knew that Pluto had a moon? How many of you know that it has 4? Sorry, 3. we keep finding them. But this is why Pluto had to be reclassified, because there are more objects like Pluto. Some are potentially larger than Pluto. We know of 5 what we now call dwarf planets, and depending on our definition, could be even as high as 9. With Rubin, we're going to find at least a few more. Depending on what the solar system looks like, it might be a lot more than a few more. And then this is the big one in the outer solar system. Oh, sorry. Before I move on to this one, why did I ask about the kids? My usual conversation in an Uber is, what do you do? I'm an astronomer. Why'd you kill Pluto? And the answer is, do you have kids? Yes, I do. Would you like them to learn the names of 8 planets or 15? And that changes the discussion. However, we're trying to add the 9th planet back. We're trying to kind of do the right thing. There could be another big planet in the solar system. And I'm not thinking Pluto. I'm thinking something as large as Uranus or Neptune, just hiding out there. And we, astronomers, have been looking for it since about 2014. So far, there are good indications that it's somewhere out there, but we don't quite know where. But it just so happens that if you have a telescope that can observe to 24th magnitude and cover the entire sky, your chance of finding this object is essentially 90%. So I'm really hopeful that we could have one of these Astronomy on Tap events in about 2 years, and we're going to be talking about the new planet. Or we're going to be talking about how it doesn't exist. So I'm going to be happy either way, because the astronomers are easy to please. But I would sure love for us to have that talk about the new planet. And that's what Rubin can do. That's what this one telescope can do. But wait, there's more. We're not the only planetary system in the galaxy. There are many, many, many more. These are just some of the planets that were discovered, and Megan and company know about this much more than I do. I think about dots and algorithms. They actually think about these things that have their atmospheres and so on. What these planets have in common, planetary systems have in common with ours, is they also have asteroids and comets. And sometimes their version of Jupiter kicks them out as well. They go into interstellar space and they're very lonely, and then they see us. They see the solar system and they say, this is so much fun. I'm going to go there and visit those Earthlings and cause them not to sleep for 2 weeks because they're trying to take images of me. These are what are called interstellar objects. The first ever was discovered in 2017, the second in 2019. We knew of only 2 of them up until about 2 weeks ago. Rubin will discover anywhere from 5 to 50 over the next 10 years. And the reason why there's a factor of 10 difference here is we just don't know what's out there. This is the most fun it can get. Like you're observing, you're exploring something that's so unknown that the error bar is factor of 50, factor of 10. So this was the 3rd one, discovered on July 1st. I had everything planned out. I was going to take a mini vacation, fix up the house, getting ready for sabbatical next year and so on. And then this thing showed up. Nobody ordered that. But it was a 3rd interstellar object. Looks like a comet. It looks beautiful. It was discovered on July 1st. And it just so happens that we're still in test mode, our telescope. But it just so happens we were observing in that region of the sky, and we had data on disk from that time. So we went back, looked at it, and found the earliest high-resolution image of this object, where you can clearly see that it's extended, it has a coma, it looks like a comet, and it's coming towards us. It's safely away from the Earth, don't worry about it. Mars will get a good look, but it's all good. Not just that, remember how I said that we take movies? There's the comet moving. So this is it. Notice how it's slightly extended. It seems like a little bit elongated. That's partly because it really is a comet, so it has a tail, but it's also partly because it's moving so fast there's a bit of a motion blur as it moves on our image. And we take 30 seconds to take that exposure. So it's that fast because it's coming out from outer space, just zipping through the solar system. So this made all of us not sleep for a while. We quickly built up an impromptu collaboration, wrote a 40-page paper in what seemed like an incredibly, non-stop 3 days of writing. This is what the author list looks like. I'm actually lying because this is the first page of the author list. There are 200 people on this paper. And these are the folks that really pushed it through. So Colin Chandler, who's the first author, Pedro, and Devanshi, who, one of the things that Devanshi did, she's one of our undergrads over there, she managed this whole list, which it's incredible that we got everyone here. But these are the kinds of things that you can do with Rubin. And the coolest thing is that this was not supposed to happen. This is just a test. It's just that this telescope observes such a large swath of the sky that whatever happens to be there, we just have it. And the reason why it's just the beginning is I'm going to show you this picture. Now, this is terrible. Like, this is the sort of thing that your advisor tells you never to show because you have to spend 5 minutes explaining what it is. But each dot here is one pointing where the telescope pointed over the last 3 weeks. This here is day 0 of the survey, and then going up, color-coded are just the days since the beginning. And for those of you who are astronomers, this is RA and DEC. These are coordinates in the sky, kind of like longitude and latitude. To make a very long story short, in the past 3 weeks, we've already imaged a third of the solar system. Remember that animation that I showed you that Jake put together? How survey starts and boom, we see a third of the solar system. There it is. It's on our hard drives. We expect about 200,000 new asteroids, hundreds of comets, maybe even a planet to be in here. That's what we're doing for the rest of the summer. So no vacation this year, or decade, I guess. So this is a heads up. Because we're going to start doing this on a regular basis, starting in 2026, look forward to something new and interesting every week. That's the really cool thing about this telescope. These sorts of things that I've shown you, they're not going to be coming every month or like every year, every couple of months. They're going to be coming every week. There's going to be an interesting object. There's going to be a new dwarf planet. There's going to be an interstellar object. There's going to be a potentially dangerous asteroids. All those things will be happening. And one of the things that I really want to point out is all of this is from one telescope. And that's the power of Rubin. It can take this one data set and it can allow you to do everything from discovering objects in the solar system to dark energy, to dark matter, to galaxies, and so on. I already spoke much longer than I was supposed to, and I barely got through the solar system part. Now imagine how much more there is behind it, and that's why it was worth building. All right, so after 20 years of development and construction, Rubin is here. Discovery engine like nothing we've seen before, and it's open to you. And I'm going to end on this. The cool thing about Rubin is that the motto of the project from the beginning was open data, open source, open science. So what we want to do is we want to make data accessible to everyone as much as we can. Enable scientists from all over the world and all backgrounds to participate, including volunteers to contribute via citizen science. And this is going to be the first time that this much astronomical data will be available to that many people. And I really encourage everyone to try to get involved in this because now, astronomy was always what's called a data-starved science. We didn't have enough data. We had many astronomers who didn't quite have enough data to work on. Things have changed completely. We have so much data that if all of us became astronomers, we'd have something to do for the next 10 years easily to discover interesting things. So if you want to go and get involved in this, here's our first project on Zooniverse. It's called cometcatchers.net, also put together by Colin Chandler. If you want to go and try to see if you can help us find a comet by looking at images and trying to see if things have tails, I'm vastly oversimplifying what's going on there, but it's kind of that. Go there, register, join the hunt. All right, so I'm going to end it here. These are the kinds of questions that we will be answering. What's dark matter? What's dark energy? What are the rarest phenomena in the universe? Ask me about wackos. How galaxies form. We're going to map the solar system. We're going to protect the Earth. And really over the next decade, it's going to be all about Rubin and its data, mapping the universe and rewriting textbooks across all areas of astrophysics. So I hope I didn't go too much over time. Hope this was interesting. Hope this was coming. And let's do it. All right, questions? Yes.
Where's the best source to get updates about findings? Like, I don't have any sort of social media. I don't want to, but I want to be able to go somewhere and have
Astronomy on tap.
Yeah, I know. I'm here.
Astronomy on Tap by default is always the best source
The
for
weekly
everything.
stuff, like you said, it's going to happen week by week by week.
RubinObservatory.org is the website. LSST.org will get you there as well. I'm sure that everything interesting that happens will wind up there. But usually, this kind of news is very broadly interesting. So you may hear about it without even looking for it. I think I had a slide somewhere in there that I took out with all the front pages of newspapers all over the world that mentioned the First Look event. And I expect if you find a planet, you'll hear about it. Yes?
If you were going to build a parallel telescope to do a northern sky survey, where would you put it?
So if we could build one at the north, where would we put it?
Yes.
So the usual answer is Hawaii, because top of Mauna Kea has numerous observatories already. The site is excellent. We know how to operate, but it's pretty busy up there. It's already overbuilt. So the other option that the project was looking at the time was actually Baja California. In Mexico, there's a really nice site. Just drive, I think, a couple of hours south of San Diego, and you find yourself there. But the infrastructure wasn't as good. I think you would probably end up either there or maybe in the Canary Islands. Like those are the typical places. But Chile was by far the best given all the constraints. Yes, there was a person right behind you. Yes.
So 20 terabytes of data a day, right? You picked a skill. The computer algorithms only know what you train it to. How do you find new things that we haven't discovered yet? How do you find the time to find them?
That's the challenge, isn't it? So one of the ways, let me talk about, so there are two parts to this. One is you look at an image and you detect that there's something there. There's a source. It's not blank sky. So we can, let's call it teach a computer. We can write an algorithm to do that quite effectively. And then, is that source similar to something else you've seen before, or is it an anomaly? Now, that's where the game is right now. You can apply all kinds of statistical classifiers that they're sort of classical nature or things that involve AI, machine learning, neural network. But things like, here's one example. You could ask we're going to see about 40 billion objects, give or take. And then you can train an algorithm to look at every single one of those 40 billion objects and tell it, classify them by similarity. And it's going to come back and say, these billion look just the same. And we're going to look at that. Oh, spiral galaxies, boring. We know about those. Oh, actually not. It would be like 100. And then you go down this thing, things like don't look like anything. Sure. Maybe you don't. So a little bit. When you have and I think it's 4 billion. Instead, we're going to be looking at the rarest things in the universe that they really are. So I jokingly said, ask me about wackos. One of the things I want to do is I want to create a catalog that I've lovingly called the Washington Catalog of Curious Objects. And that's going to be it, basically. Let's try to see if we can find things that look anomalous, that are groups of things that look, groups of things that don't look like anything else, and then we're going to go and try to figure out what they are. Yeah. All right, I think there was a hand up over there.
How are you making decisions
It's closer to the latter when we're choosing topics. So the way to think about this is going to be like, these are huge images and huge data sets, and you can do a lot of different things from the same data set. It's like, and I'm going to be making up analogies on the go, so this may be a total disaster, but think about it as we're in a savanna and there's a watering hole. There's a lot of water. Different animals come to drink water. They're interested in different things or scared of different things. They're going to do it different ways. It's a similar thing with this research. Somebody may be interested in supernovae, these stars that explode. They have a group of 10, 15 people who they collaborate with. They're going to use that data set to find supernovae. We're in, let's say, interstellar comets. We happen to have a group of 200 people we're collaborating with. So we're going to focus on interstellar comets. And then within that large group, there's a subset that cares about what the comet looks like. There's a subset that cares about how it travels through the solar system. There's a subset that cares about where it came from, and so on and so on. Management is not easy. Honestly, this 200-page monster, 200-person monster was the first time we've done anything like that. I'm just amazed that it actually worked, but it works. We were able to go from, hey, look, we have that object, to, hey, look, we understand what we're seeing in about 3 days longer. The thing that I really love here is that this is really us downloading the sky. And then anyone here can, if you have a good idea what you can do, you on your own, or you plus your friends, or you can advertise the project and build a collaboration, can go and try to find it without having to ask anyone. So that's what I love about this project. There's really no hierarchy. There was a hand up in the back. Yeah, let's go with you. Yeah. Yeah. Yep. That's exactly the thing. The Rubin telescope just goes and maps the sky and doesn't care about anything that's happening in the world. It's happily mapping the sky in a predetermined pattern. All of that goes into the database, and then all of us feed off of that database. You don't have to ask for time. Yeah, you don't have to ask for time. It's like giving an 8-meter copy of everything that's happened in the sky over the last 10 years to every astronomer on Earth. That's the way I think about this project. Another nickname I have for it is Google of the sky. We want to index everything that's in the sky. You go and type your query and find interesting thing. All right. Oh, so many hands. Let's see. I think a lady over there had her hand up. Yep. Oh, what would we like to find? What would I like to find? I'd like, right now I'm in a phase where I would just like to find that everything works. We're working on it for so long and spent like $1 billion of your money. So thank you, by the way. It's all taxpayer funded, other than the initial private investments. But no, joking aside, I mean, this is serious, it's not a joke. We still have 6 months to make it fully work. I'm most interested in the solar system right now. So I would like to know how solar system began, where did the planets form, and then what happened in the first, let's say, half a billion years of the solar. Because it's not obvious. Like, we think of the solar system as, there are 8 planets, they're in their orbits. Every morning or every evening I go out, I see the planets, and it's been like that for billions of years. It actually wasn't. We didn't start that way. It seems that all of us were crammed about factor of 2 closer to the sun where we began. And then for some reason, solar system expanded. Uranus went out, Neptune went out. It's even possible that the two may have shifted places. It's possible we had more large planets, they got ejected. All of that right now, the details of it are uncertain, and we think we'll have the data to be able to answer them. So I think that will be quite interesting and profound to be able to answer, where did Earth do 4 billion years ago, and how it all went. It's a yellow shirt there. Yeah.
Is it sensitive enough to measure the Oort cloud?
No, Oort cloud's too far. However, Oort cloud sends comets to us occasionally. So virtually all those comets that we're going to see are visitors from the Oort cloud. That's how we'll know what's going on out there. Yes.
You measure the variability of individual stars in the brightness. Does it measure the variable brightness of large fields to see like interstellar gas or intergalactic gas?
So those don't change that quickly. And you know, there are reasons having to do with basically causality and finite speed of light. Like they're so large, they seem small to us, but they're really so large that if they change quickly, you know, you'd have to have this region that's 10 light years away from there somehow communicate. So those don't change. The places where things that are diffuse change are actually our solar system. We're going to have something called the solar changes as the sun change. If you have a galaxy nearby, the galaxy that's for shapen, but the intensity of it changes depending exactly on the geometry and what's happening in that background galaxy. But usually it's points that change, either change their brightness or move. All right, there's a question there.
So it's a 10-year survey that took 10 plus years to build, and certainly time before that to plan. What's next? Do you wait for the 10-year survey to end before there's already the next planning phase, or is it already in motion? And if this is such a grand plan, does it risk taking away the impetus of next?
So the way this usually works is these large telescopes take a very long time to build, as you said, and then for the first couple of years, you just want to use it. You don't want to think too far in advance. And the reason for that is, you know, I've told you all these stories about what we're going to discover. If I come here 5 years from now, I'll probably tell you that we've discovered a lot of those things, but the headline probably will not be any of those things. It'll be something we didn't expect at all. And that's what's happened with the Sloan Digital Sky Survey. So Sloan Digital Sky Survey, when that started, nobody really had a notion that there are going to be dozens and dozens of small dwarf galaxies that essentially consist of only of dark matter, or that there are going to be stars that were ejected by our black hole in the center of the Milky Way and are like traveling at 1,000 kilometers per second out of the Milky Way. So you want to spend the first couple of years of having the new observatory really understanding what is it that is telling you about the universe, because then you know what to plan next. Because the most interesting thing that you want to build your next instrument for may not have been discovered yet. So the way this is likely going to work is we're going to be very busy next 3, 4, 5 years. By then it'll become clear what is it that's most interesting for the next phase, and then people start thinking about the next phase. And then I just really hope that we find a way to accelerate these phases, because you know, 2 decades is getting a bit too long to build telescopes like these. Yes? Yes? Sorry, are you asking about storage?
Yeah, what type of storage? Is it like cloud, data center?
Yeah, so we have, I ran data management, so I have to be careful, as otherwise you'll be here until tomorrow if I start talking about this in detail. We have a data center at SLAC National Lab that's in Menlo Park, California, right next to Stanford. And so it's a fairly classical data center, you know, racks of computers, racks of hard drives. I think there's a tape library there. I'm not 100% sure. But in terms of storage, it's fairly kind of usual on-prem stuff. The user side of things, so that's where we do now processing of images, like detecting which objects are on the image. Then we have a user side of things where we serve those users to do static class. So we keep that on the report to the American headline to finish your presentation, and suddenly your load goes up by a factor of 10, because everybody at the same time is trying to finish their papers right on time to deliver them for a conference, which is why the cloud is a great solution for this, because then you can scale up and scale down. But for the rest, it's much cheaper to have it on-prem because we know what our load is going to be throughout the year as we're processing these data. And we can talk until the morning. Yes, right next to you.
So there's the 10-year plan in terms of what's going to be the next big thing to build. There's also the what happens to the telescope in 10 years. Is it like a Mars rover where it keeps going, or is it like, oh, we fill our hard drives and that's that?
It'll keep going. I think if everything works as expected and if the last couple of weeks are anything to judge by, they will. It's just it's a telescope that gives you situational awareness of what's going on in the universe. That's the way I think about it. You can just have the entire sky at the palm of your hand, any astronomer. It's incredibly cost effective. And you just keep doing it. You'll be upgrading the instruments. That camera 10 years from now is going to be maybe outdated. We're going to put something better. But the general concept, give me something that can tell me what's happening in the universe at all times is a sound one. We always want that. All right, let me see. I bet that there was someone who's had their hand up all the time and I just missed them. So if you're that person, have your hand up. All right, Ishan.
So the picture served the first look with the commissioning camera. How much more impressive is LSST camera?
Oh no, first look was LSST camera. Yeah.
So do we have, how does LSST camera compare to the commissioning camera that's getting additional?
All right. So this is a little bit of inside baseball. When the telescope was first built or finished, we started with something called commissioning camera, which was a very small camera just to test that the telescope works. And what Ishan is asking about is how bigger or smaller is the camera that I just showed you from relative to that one? 21 times larger. So the commissioning camera, which all of us were really impressed by, scientists, was 21 times smaller than this one. So yeah, this is much bigger. And it's about to get a lot bigger. Again, remember, 0.13% of the entire sky of the footprint is what I've shown you.
Sounds like you're vacation again.
No vacations.
All right, let's give them another round of applause.
Thank you.
Trying to fix my mic. Okay, yep, there we go. That was great. Now the moment you've all been waiting for. I'm kidding. Okay, trivia answers. So we have one person or people who got 8 out of 10 right, and 2 people who got 7 out of 10 right. So I'm going to go through the answers, and then I'll reveal the winners, and you guys can, since this is our only talk of the evening, you just come right up and get your prizes and a handshake from Mario on top. Okay, first question. It is located in Chile. Hopefully you figured that out by now. The LSST is planned to run for 10 years, but it's going to run longer. The size is 8.4 meters, or how many feet? 24. Okay. 20 terabytes of data will be taken per night. 5 million main belt asteroids will be being used. Frequent sky coverage is what helps us to detect fast-moving objects. The field of view on Rubin's camera is 9.6 square degrees, or how many square inches? I'm just kidding, it's degrees. Okay. Rubin's going to survey the entire visible sky every 3 to 4 nights. And lastly, it can detect interstellar orbits. Also happens to be something we'd love to discover. And the second runner-up is oh God, I don't know what you guys wrote here. The Vorwerp? The Vorwerp? Does that sound familiar? Okay, I did not understand the reference. Okay, and then the overall winner with 8 out of 10 right is Sneaky. Who was that? Come on. You're not astro majors. Didn't you write a bunch of papers? Not yet. I don't know. What do you think, Mario?
We'll let it pass.
Okay, we're gonna let it pass this time. Okay. Alright, so now that's the end of Astro on Tap. We're gonna have one next month, if I can find a speaker. And that's gonna be on August 27th at 7 p.m., same time. And then there's gonna be one in September, and Sam's gonna take over as leader. It's gonna be great. Yeah. Okay, so if you got prizes, come get your prizes, and otherwise get home safe. And thank you guys so much for coming.
We were supposed to ask you about wackos.
The wackos.
So that's part of this. So that's the we're trying to, like somebody asked about